Have you ever tried to run a really massive simulation? I'm talking, fluid dynamics or maybe billions of particles interacting.
Oh, yeah.
You realize pretty fast that your computer, it really struggles to roll a truly fair die.
It does. We're always relying on these pseudo-random numbers, these fake random numbers.
And before 1997, engineers were hitting some serious walls. The patterns were just emerging way too soon.
That's the computational roadblock. And it's exactly why our deep dive today is on a masterpiece of engineering, the Mersenne twister.
The MT, right?
Yeah, developed back in '97 by Makoto Matsumoto and Takuji Nishimura. And they designed it specifically to eliminate the flaws in all those older generators.
Okay, so just how big was this fix? I read the period length. It's based on a Mersenne trime, 2 to the power of 19,937 minus 1. That number is just staggering.
It is truly staggering. I mean, to give you some scope, its period is orders of magnitude larger than the estimated number of particles in the entire observable universe.
Get out of here. The whole universe.
The whole universe. We're talking something like 10 to the power of 87 particles. This scale, it just guarantees the generator won't repeat a sequence in, any practical lifetime.
That sounds like overkill.
Yeah.
But practically speaking, what was actually failing in the old generators that this fixed? Was it just that they were repeating too soon?
That was part of it, but the quality was the real problem.
The quality. Cool.
Older generators, they suffered from what's called low-dimensional distribution issues. They might look random if you plotted them in 2 or, say, 3 dimensions.
But if you go higher...
Exactly. If you group the numbers in higher dimensions, you'd see these clear, obvious patterns. The MT solves this with high K distribution.
Right, I saw that term. It's highly well-mixed.
Extremely well-mixed, up to 623 dimensions, which means every possible combination of bits occurs almost equally often. The patterns are gone.
I saw some really technical terms like twisted generalized feedback shift register and a temporine transform. That sounds like pure math.
It is. But think of the register part, the TGFSR, as the engine. It's producing this long, very complex string of bits.
Okay.
The tempering transform is the final crucial step. It's like a polishing layer. It just guarantees that the output bits are completely mixed up so those hidden patterns are totally erased before the number ever gets to your software.
And that mathematical rigor, I mean, that's what won the adoption battle, right? The list of programs using it it's just mind-boggling.
It is.
If you've run Python, used MATLAB, or even just opened Microsoft Excel lately, you've used the Mersenne twister.
Yeah.
And it's fast.
Oh, it's incredibly efficient. Implementations are often something like 20 times faster than hardware methods like RDRAND.
Wow.
And that adoption, it just shows that when you solve a foundational algorithm with this level of excellence, industry changes fast.
Yeah.
If you're building systems that rely on this kind of cutting-edge tech, whether it's for simulations or integrating advanced AI agents, you really need a partner who understands where to apply that power, which actually is a great moment to mention our sponsor, Embersilk. Absolutely.
Need help with AI training, automation, or software development? Or maybe you're just trying to figure out where agents could make the most impact for your business. Check out embersilk.com for your AI needs.
So getting back to the MT, while it is a triumph for simulation, we do have to mention its one known limitation.
Okay.
It is not cryptographically secure. For real security, you can't use it. After you see just 624 outputs, the future becomes completely predictable.
But that's not a dead end, right? It's more of a design challenge that the community just solved. They didn't abandon the idea. They built on it.
They absolutely did. They came up with CryptMT, for example. It's a variant that is cryptographically secure, and it uses the Mersenne twister internally.
So they fix it, and they also made it faster. I saw something called SFMT.
Yes, the SIMD-oriented fast Mersenne twister. It's roughly twice as fast, optimized for modern processors, and it improves throughput significantly.
And they even made a tiny version for when memory is tight.
TinyMT, yeah. It reduces the state space from about 2.5 kilobytes all the way down to just 127 bits. It just shows how adaptable the engineering is. There's a version for every need.
So when you connect all this to the bigger picture, the Mersenne twister is really this pinnacle of computational math.
It really is. It provides that reliable, high-quality randomness that powers so much of modern science and development.
So what does this all mean? The fact that we could create and then continuously improve such a complex and fundamental tool, our ability to engineer high-quality artificial randomness. It just underscores our capacity to build these intricate digital worlds and to constantly solve even the most abstract problems we face. We build the tools, then we make them better.
That adaptability is our strength.
If you enjoy this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.